I'm Carl Fedrowisch, KG5NXY. I'm a new ham. Uh, my background's computers. I started building computers around 1977. I've worked all over the place. Worked for Intel for about 5 years as a consultant. Worked for Tektronix, while name dropping. But I had been interested in radio ever since a kid because, of course, I started taking it apart like everybody else here. and then I used radios. I got interested in ham radio, but nobody around me would help me learn code and blah, 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 blah. And so anyway, I didn't become a ham until a couple of years ago when I got interested in building a satellite, a CubeSat. And it turns out you have to have a ham license to be able to get it licensed. Who knew? So anyway, I went and got my license, and then I found out, wow, there's this great group of people in this area around here called hams, and I didn't even know I knew, didn't really even know any hams here in Slidell after I moved back. So anyway, that's my background. I'm a real tech geek, and today we're going to talk about software-defined radio under the hood, okay? Because everybody knows what SDR is, right?
Yep.
Yeah. Everybody's got one. Paid a lot of money for it too, I bet.
Not everybody. No, almost 50 bucks.
Okay. Let me ask y'all a question. Who among you actually has a standalone SDR type radio? Like a Hacker RF or something? A couple of guys?
Well, that's the question. Today, so many radios, they have all sorts of software in it. So
okay, what I'm talking about is something that plugs into your computer with a USB port.
Okay.
Anybody got those?
I got
1, 2, 3, 4, 5. Okay, good. Well, today we're going to talk about this one, which is a receiver only, the Rtl-Sdr, which costs $22 on Amazon. And it goes from 30 megahertz, well, about 28 megahertz, up to about, I don't know, 2,500 megahertz. But of course, you can get them. SDRs are not limited. The Hack RF that I mentioned before has transmit as well as receive and operates from 100 kilohertz up to 6 gigahertz. So if you're really interested in wide band, get a linear for it, and you're all set. Another thing about these is that they've become not only cheap, but they're quite sensitive. And by the way, we're getting some feedback here. Okay. So today we're going to talk about this particular module again. Well, all right, first off, let's talk about the difference between radios and SDRs. Radios, as we all know, have multi-stages. We're all used to having an RF stage with a mixer that injects a signal. Then we have an IF stage where it's amplified. We have double conversion receivers. But when it comes to these chips, people weren't really thinking about it at first, but computers are so fast. I'm sure everybody here has got at least one machine that runs over 2 gigahertz. And so if you're trying to deal with 30 megahertz, the computer's got plenty of time to do all kinds of stuff in time between cycles even. So that's the basis of SDR. The actual chip that they use, the RTL, 2832U, it means it's the U stands for USB, but it's a chip that is basically a wideband detector. It's got a it's supposed to have a 30 megahertz bandwidth, okay? 30 megahertz, which means you can look at an entire spectrum very easily with this chip all at once. This dongle chip was originally designed to work for television sets and plug in TVs. And what happened was they incorporated an FM radio, and it actually had some different circuitry in the FM radio than they did for the DAP, DAP, whatever TV. And this one engineer was writing a Linux driver for it, and I don't have his name, but it's in the presentation. And he found that, wow, I can take this FM signal, the and program it to anywhere in the spectrum. So that was about 7 or 8 years ago when it's first, these very inexpensive SDR radios started coming out. And there were several people developed it. There was a lot of different software, standalone software that worked on it. But then some people got together, some Linux people, and created a thing called GNU Radio Companion. And if anybody's used Linux, they know GNU is like one of the GUIs interfaces and stuff. But anyway, it applies to a lot of things Linux. And GNU Radio was funded by one person for about $300,000 or so, I believe, to actually get a package together. And GNU Radio is free. When you install it, it's got sections for different types of SDRs. There's like about 8 different ones. And they have some standalone programs that you can just click on and bring up your SDR. And but they also have a thing called GNU Radio Companion. And I'm kind of getting ahead of myself because that's what we're going to talk about and demo at the end. Anyway, let's get back to the software-defined radio because I think I lost track there. Anyway, in conventional ones, we know we're used to multi-stages and we have everything, but we only have one stage, literally. They call it, you've heard of superheterodynes. Well, this is a monodyne or a homodyne or there's a couple other names they call them. But what it means is it has no front end to speak of. It's just, if you want to, you can actually directly send a signal to this chip and it can demodulate it. And of course, really what I want to talk about today is demodulation, modulation and demodulation, but I'm just kind of hiding that part. Because that's really what all radio is all about. How do we incorporate a signal into a radio? And of course, with digital, we can do a lot of things that, were previously done in hardware. So anyway, the other component of this dongle I need to talk about is the front end, which is the thing that actually gives it the wide range. It's a TV tuner, and I forget exactly what it's called, but it plugs in front of the Rtl-2832U, and it's the thing that gives it the wide band capability. But it basically takes whatever signal that you've tuned it for and brings it down into that 20 megahertz output and feeds that to the Rtl-2832U. Now on this unit, you cannot receive low frequencies. It has a cutoff at about 28 megahertz. I have actually been able to pick up Citizens Band on it, 27. But anyway, that same dongle, though, can be made to operate at a much lower frequency by basically going around that front end chip, the tuner chip, and feeding your radio signal directly to the Rtl-2832U. So there is a modification for this thing that'll let me operate it at 160 meters or 80 meters or AM radio even. But most times that's not going to come into play when you use this. Most people aren't going to take one of these things apart, even though they're cheap. They'll just buy another one that has that capability. And I think they're beginning to make some like that. All right. So what we're going to do now is explain a little bit about digital signal processing. And I guess this will make a lot of sense when I do the demos. I think I just really kind of ought to skip just straight to the demos because is anyone familiar with the IQ signal? A couple of people, okay. In radio modulation, there is a thing called quadrature. Quadrature means that there's two signals that are 90 degrees opposed. And this is the basis of all modulation, whether we realize it or not. Because it's called the IQ signal. You take the original signal, they take it 90 degrees out of phase, and then they use it to mix in audio or digital or whatever, and you can get quite sophisticated. Just using the IQ signal, which is all that is available on the FM portion of this dongle, you can do any kind of modulation, or demodulation, I should say, on this radio. And they do it with software, and like I said, the computer's plenty fast enough for the most part to do these things. Well, with IQ signals, you're able to take, since I said it's two different signals that are mixed together, it's pretty easy for me to show it. I really should. Kind of skipping around here, but a little thrown off here by this lack of a projector. And I thought this would be the case, that it was actually easier to show things than it would be to... All right! When I first plugged this Sdr module in here, it didn't work. I was kind of upset, but I thought, well, come on, guy, you're a ham. Figure it out. You know, nothing works at first, right? Okay. Oh, this is wonderful. All right. Well, then let's see if we can find the presentation where we were at in our presentation real quick and show you some pictures that... Well, since it's up here right now, I'll show you. This is what I want to bring across, is this is a example of two different signals that are being sent to, that are mixed together with a GNU radio companion. And as you can see, the scope output is at the top, and bottom, you can see two distinct frequencies. There's one frequency is at 800 hertz, the other is at 1200. This bottom is a fast Fourier transformation plot. For those of you who may not know what FFT stands for, it does stand for fast Fourier transformation, but it's a means, a mathematical means of taking a signal and deriving the component frequencies from it. So in other words, this is how basically things are demodulated. They can actually take a signal, break it up into its component signals. In this example right here, I'm showing you the Fft plot, and I'm also showing you a scope plot of what it looks like. Now as I change, there's a slider here that I put on top, and you can see actually how, as the bottom portion there, the peaks change. You see it's got narrower, closer together, and now they're almost merged, and at top, when the two of them are on top of each other, you'll have a perfect sine wave. But anyway, this is just, we don't want to get ahead of ourselves too much on this. Let me go back to the presentation, now that we can do that, and find our spot. There you go. This ought to be good enough to start with. All right. So this is what we're used to, right? This is a bad drawing of SDR. I really don't care for it because it's got a lot of things in here which are actually not into this unit. What can I say? I have AD. You know, basically, though it's true, you have an RF front end. You have an analog to digital converter, which converts the signal into digital. In this case, it's like I said, about 25 megahertz wide, 8-bit deep. And then this processing over here on the right on the top part of the diagram, and yeah, you got all that stuff, but this is more likely you'll find that in an ICOM receiver. So in any event, this is the, again, this is the tuner I was telling you about, the Rtl-2832U, and this is the device number so that when it does a USB thing, it can be picked up. I almost missed this most important part of why SDR is such a good thing and why we need it. It starts with radio transmission problems, okay? Plus, of course, our bands are getting pretty crowded. And, but the problems with radio transmissions are that they're, line of sight. and we have different ways that radio reacts to the environment. We have ground waves, we have sky waves, and just like light, we have reflection, refraction, diffraction, which is where it curves to follow the ground, absorption, and we also have polarization. And I apologize for polarization there. You may not be able to read it, and it's even worse now I see. For some reason, when I converted this over, some things got highlighted like that, and I don't know how to make them normal. In any event, it's a zoo out there because all this causes scattering, different effects, are from meteors, which I'm sure everybody knows is used for weather data is being transmitted because of meteor showers, gives them a little place to reflect, and they've been doing that a long time. And there's aurora backscattering, propagation E, sporadic E rather, propagation, troposphere, rain, airplanes, lightning, and what it does is it causes your radio signal to fade. And also, there's multiple paths in our environment because we have radio in cities, it bounces off of buildings, trees, cars. So what happens is the signals arrive, the same signal can arrive from two different directions, say, for instance. And what that does is, if you look at the effects on a digital signal at the top, you'll see how you have your symbols that they send are set up so that there's a guard interval, which I'm pointing to, which is hard to see, maybe, the cursor works, that thing right there. It's a blank space between symbols. But what happens is when you have phase change and reflectivity, those overlap, which means you're going to have some problems. And this is where software-defined radio really shines, because it's all garbled to us in our ears, but computers can sort it out. So a couple of things they've done is, as the bandwidth increases and things get more crowded, they need to have multiple subcarriers, which is just another way of saying multiple lines. If you were using a computer data line, if you wanted more bandwidth, they'd actually give you an extra phone line. I just recently had that. We just upped our AT&T line, and they had to go back and add a second phone line, literally, to give us twice as much data flow. And they do the same thing. They have multiple subcarriers, which means you have additional portions of the front end. Okay, what happened here? Yes. Anyway, now we're getting back to the this hardware thing, talking about the Realtek Rtl-2832U, which is the heart of this particular SDR, and this is a DBV-T COFDM demodulator. DVB-T stands for Digital Video Broadcasting Terrestrial, and COFDM stands for Coded Orthogonal, I guess, Frequency Division Multiplexing, and U stands for USB 2. Anyway, this is some more things about this particular chip. It's got the DAB, which is the TV portion, and it has an FM demodulator, and it outputs an 8-bit IQ signals, which doesn't sound like a lot, but it is. 8 bits is more information than you would think. Anyway, and these are the limitations of it. It's designed to be about 3.2 megahertz, but in actuality it's about 2.5. Sample rate per second, rather. Anyway, it's got some other stuff in that chip, which is kind of interesting. This is the chip, or this is the SDR I've got. This is my homemade adapter, so I can hook it up to my 2-meter antenna. And haven't really get out a good way to. I built it in about 10 minutes. It really needs to be shielded, but it works fine. And this is the inside of the dongle. And like I said, it's not really hard to go in and change it for low band use. There's some soldering that needs to be changed on the input here. You basically reroute around this first chip, which is the tuner, which gives you that wide bandwidth from 30 megahertz on up to 2 gigahertz, and feed it directly into the second chip here, which is the RTL 2832U. Okay. Blah, 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 blah. Okay, let's see. This is also called a 0IF type of receiver because it doesn't have intermediate frequency stage. There's a lot of different things here about the chip, if anybody's interested. If anybody's interested, by the way, I do have a PDF of this speech with a lot more additional information, a lot more reference information, which when we find a way to make it available to you guys, if you want it, you're welcome to it. If you have a flash drive, well, that's not a good idea, but I was going to run a web server off this thing. I never got around to it. This goes into a little bit about the chip, but we already talked about it. And this is actually the schematic. This is where the work's done. Okay, now look at this, guys. On the input side, on the left here, you have an analog to digital converter, and if you look at it, its clock is 28.8 megahertz. That's pretty fast. It's a special type of A to D converter called a flash converter. Flash A to D. Oops, went too far. Oh, now we're lost. Okay, and they do list here as a IF, but you can see that what it does is it feeds into a separator, will you? I don't know. But this is where you get your IF signals, and they are then fed into a resampler, which breaks down how much it looks at. We're going to talk about that in a minute. And if you'll notice here on the far right, there's an FFT output. This is where, again, it takes a signal and breaks it up into its components. And then software does the rest. And again, more information on the chip. I think we covered it pretty well. This is the history of the chip. And Eric Fry was the guy that discovered the fact that you could program the FM portion of this chip to make an SDR in 2010. And then Palisari started popularizing it, and they put together him and Steve Markgraf. They're actually not together, but they got a working SDR. And where did I have about the? Okay, something's out of place here. But anyway, I thought I had in here the guy that sponsored making GNU Radio. That's right, I have it back there. But anyway, this is the front end, the digital tuner that I was telling you about, the other chip, and it's pretty simple. It just has an RF in, and you have a automatic gain control, and it doesn't really show it, but you have some programming lines here to program it. And this is actually being done by the Rtl-2832U because it has a USB interface. So it does whatever the computer asks. This is the front end circuit simplified, and I'm not going to go much into it. There's not much here that, well, it's pretty geeky, and to be honest with you, I'm not sure exactly everything on it, but I thought I'd show it to you anyway. That's what the internals look like. And we have some specs here, and we have, now we're back to IQ signals. And what is an IQ signal? Well, it's a synthesized signal from 2 amplitude modulated sine waves, basically. And, oh no, what is happening? Oh my computer's gone crazy. I'm sorry. I'm having, all right. Yeah, I know. All right. So this is a picture of 2 sine waves, and you know, everybody's familiar with this, right? Because we all had to deal with impedance, AC resistance, right? And we all know that, you know, current lags voltage.
Eli the Iceman.
Yeah. So it's not too far different than that, and we see that in regular signals. And again, quadrature just means that two sine waves start off at 90 degrees apart, and it's a scary thing. And if you don't know it, they throw it around. Orthogonal means 90 degrees apart. All these big words. Why don't they just say 90 degrees apart, right? We all know that. Okay, so now this is an important diagram right here. We start off with two signals, and those are the dark blue and the dark red lines. And the actual signals that are produced from it are these little very faint lines. You're supposed to be able to see this. In any event, it's on the next page maybe. Nope. All right, well, there's a very faint blue line, and there's a very faint red line, and those are the two signals, the IQ signals that are produced by these two sine waves. Just wanted to show you how they all kind of are represented. Yeah. Okay. Now that everybody totally understands how the hardware works, we're going to go to the software portion. And like I said, GNU Radio is a free software package that works on most everything. I even got parts of it to work on a Mac. But it was created, GNU Radio was created by philanthropist John Gilmore, who gave $320,000 to Eric Blossman for creating the code and project managing. And the way GNU Radio works is it has flowcharts. I don't know if you guys ever took computer courses. Way back in the day, they used to use flowcharts. They show you, how if this, do this, blah, blah, blah. Okay. Well, GNU Radio allows you to do a lot of different things. There's a lot of different modules, and some of the examples here show you can have a scope output, you can have a phase diagram, you can show spectrums. You can do a lot of different things with GNU Radio, and it's in its simplest form. This is an example of a 2-meter. I believe that's right. No, this is the no other. Anyway, I have a couple of these things I'm fixing to run, so I'm not going to try and bore you too much with them. But this is basically what the program looks like, and it has in the upper left-hand corner the flow chart. And these components here are modular. They're over on the right-hand side. As you see, on the right-hand side, you can choose any number of components. There's a couple of caveats. There's two actual, the program generates Python code. Python is a computer language. It's an interpretive language, which means you can change one line and run it. You don't have to recompile or spend a lot of time waiting for the computer to generate the bytecode that it runs. And if y'all haven't used Python, I'm sure the Pi guys have. Python's great, and I've been using it for 15 years, ever since the beginning, and I'm really amazed at that. Everything's done in Python nowadays. It's simpler than BASIC, but then again, it's more sophisticated than, probably one of the most sophisticated languages out there, because it can be used for anything, particularly AI. Almost everything involved with AI uses Python now. Okay, so this is what a flowchart looks like, and then we're going to go into some of the components and stuff in a second. And what was I going to say? Okay, getting back, let me remind myself. Down in the lower left-hand corner is a running description of what's being generated by the program and as it interacts with Python, because it literally, when you click on the run button, it generates Python code. Then it runs it in this environment. But you can do several things. You can export the Python code, and you can modify it and put it back in there. You can actually make your own modules out of Python code and incorporate them in there. But that's a little advanced. I haven't really got a chance to do much of that yet, but the day's coming. Okay, so this is the flow chart for a NOAA weather radio. And I don't really expect to be able to pick up much, but we're going to give it a shot. It's probably easier for me just to go ahead and run it, but these are the kind of displays that you can get with it. Okay, now on to the real thing, into the slideshow. Yay. Wish I could figure out how to get this to minimize. Let me grab this. Why is it off the screen? All right. I don't want this either, but down one. All right. This I showed you was a very simple flow chart. It takes, first off is, the way you operate it is you grab components from the right-hand side, drag them over. Then you click on a box from the output side and drag a line over to the input side. And commonly things like, whoops, no, it's not going to let me do it. Simply not. It lets you drag things around and sort them out, but each one of these things has a different use. This right here, options, brings up a little window where it sets the frame for the that you're going to be working in, the overall. And there's two different types of graphic user interface modules or systems. There's, I forget now, it's WX and I forget what the other one is. In this case, because I wanted certain graphic components, I had to use the WX modules, so all my examples, but they're trying to phase it out, so for what that's worth. Anyway, this right here is WX GUI. If you were using the other one, which is I think is QT or whatever, yeah, QT, you just change it right there. And that sets kind of the standard of what modules are going to be usable in this particular flow chart. Okay, this is our signal source, and double click on it, it brings up a panel. As you can see here, it says waveform, cosine, but you can make it pretty much any kind of waveform, constant, sine, cosine, square wave, triangles, or sawtooth. So that's kind of nice. You can change things that way. The frequency, in this case here, I've got a thing called frequency slider 0. That's a GUI element. You saw me moving that little slider at the top bar. That allows me to change the frequency on one of the modules that are creating a signal. If you look at this one here, the other one, oh yeah, and the other thing about it is, well, where's my mouse? Oh, there it is. It references a variable and, I'm sorry, a slider. This is the slider, the little graphic component you saw at the top. And if you look here, it has a default value of 800 cycles. It has a minimum frequency of 0 cycles. It has a maximum frequency of 2,000 cycles. And it's broken up to 100 steps. So each step would be basically 20 cycles. And you should notice also right here that the, well, this is not a good one to show you. I'll show you that in a second. But the way it works is you have two signals. They go to a thing called the add module, which pretty simple. You really don't have much to change with it. Just plug the two in together. And then the output of that is fed to a thing called a throttle. And what the throttle does is it literally throttles back the amount of information going through, because you might want to scale your data. In other words, it's such a wideband thing. You'll find this is one thing about SDRs, is circuits are, half the circuitry in there is taking and breaking things up into smaller and smaller pieces to get to what it is that you actually want to see. Okay, and
Is that what they call decimation?
that's right. That's right. And but this is not a good one to show you. I'm going to show you a better one than this. This is just a throttle. which I'm going to change the subject just for 1 second here. Nick and I worked together at the community school in Macomb. He put together a radio course, and I got a chance to teach a section of it. But I really didn't know that much about SDRs when he asked me to give this speech 4 months ago. But I'm a quick learner, so, and plus I knew the computer side. I really thought that I was going to actually come here and write a Python script and show you guys. You would have been so bored. So much to my surprise, I found GNU Radio, which does everything I wanted to do and more. And then the other part I was going to say was Nick asked me, he decided to take the plunge. He wanted to get into learning code. He was going to get an Arduino. And after I thought about it, I sent him a long letter saying, what you need to do is get GNU Radio and hook it up to your computer and get you a $20 dongle. And you can learn Python. And guess what? You can actually build radios and stuff right out of the box, which is what I'm going to show you next. So then the other components after that, we have some output. Those two boxes we had, one is the scope sync, which is just like an oscilloscope, and the other is the FFT sync, which I explained what that was a minute ago. So when we run it, if it runs, if it's not already running, it is already running. Okay? At the top we have the scope. At the bottom we have the fast Fourier transformation plot. And again, we have this little slider here that I put in to change the frequency. And as I change it, you can see how the bottom sine waves, or cosine waves, I think, are merging. So this slide is basically my modulator. And you can see how that works in real time. But enough of this. Let's get to some real radios. As I showed you earlier, this is a NOAA, and this is one of the bad problems I have with this, is unfortunately I can't get the whole thing on one screen easily. Okay, we'll try this. All right, now we have a new component. We have the radio, the Sdr module itself. So we're going to click on it. This is what it looks like. First we have the ID, which is the source. And we have an output type, which is very important. One of the things about these, if you notice that they have little blue boxes for the output of this, that shows that it is a complex float 32 number, but you can have different kinds. This one won't let me have anything else, but anyway. And they have things like the sample rate, center frequencies, various settings, which I'm not sure what ppm is exactly. I should know that. And things like a DC offset. There's a bunch of stuff you really don't even need to worry about, to be honest with you. Pretty much all you have to do is set your sample rate and your frequency. And in this case, we use a chooser frequency, which is a graphics drop-down menu type item that I'll show you in a second when we run it. Okay, so what we have at the top are these variables, and this is the one that, which one is this? This is the sample rate, which says 250E3, which is 250,000 times a second it samples the radio. There's a list of stations in the drop-down menu. This is where they're stored in this variable called the NOAA stations. There's a variable up here, and you can see how easy it is to change them. This is these are the labels for those things in the drop-down menu, and then this is gain settings. Okay, never paid much attention to that. All right, so what happens is, going from left to right, signal comes out of the SDR, goes into a low-pass filter. Well, it goes into several things. First off, it goes up to the top and go into a frequency sink and a waterfall sink. Then the same signal goes through a low-pass filter with a decimation of 1 and a gain of 1, and kind of just basically massages the data because it's not really changing. Decimation is where, for instance, you had 16,000 signals and you decimate it by 4, you actually end up with 4,000 signals. And then they have interpolation where you can go the opposite direction. You can take 4,000 signals and make it look like 16,000. And that's all done with the this thing right here next to it called a rational resampler. And it has an interpolation of 16K and a decimation of 250K. So what that does is just modify the data flow from one, change the bandwidth basically. And then the next component is a NB FM receiver. That's a narrow. Tell me what's wrong.
The mic's on that side of your, when you turn your head. Just fine.
Thank you. Okay. Narrowband FM receiver, which is what we use in ham radio, okay, as opposed to the wideband receivers used on FM radio, commercial radio. And so this is a module for that. And at one time I told Nick I was gonna make a TV set, and then I found out that I couldn't really do that because I didn't have the bandwidth. This thing didn't have enough bandwidth for current television. It does have slow scan television though. And by the way, there's hundreds of examples of all this stuff out there. You basically download it, and you have what's known as a GNC file, and you just load it in and run it. I mean, modify it to your taste. Okay, and so the output of that narrowband FM receiver, if you notice here, it's got a thing called quadrature rates. These are some settings here that are audio and the quadrature rates. I'm not really sure, but you pretty much have to use these numbers with this particular example. It's like 16,000 for the audio and 16,000 for the quadrature rate. Okay, and then we have a high pass filter with a sample rate of 16K. And you notice one thing about these two. If you notice that going into it, it's blue, and coming out of it, it's kind of orange. Well, that's because it changed the data types. And it went from a 32-bit complex to a, does it even show me what it is coming out? Okay, let's see. Let's look at this one, because this is just a plain floating number. The orange is just a plain floating number as opposed to a complex number. Complex numbers have irrational values as well as rational values, such as the square root of -1. Anyway, so after you go through the high pass filter, we feed it to 3 different boxes. One is a frequency sink, an audio sink, and a waterfall sink. And the audio sink's actually complex. Actually, you can get by without a lot of this stuff if all you're going to do is look at the signal or process it. But you actually have to go through all of this narrowband receiver and the rational resampler and stuff just so that you can make it into audio. And so without further ado, we're going to run this radio. And we push the button. It takes a while for Python as you can see down here in the lower left-hand corner, it's generating responses, and it tells you what it's doing. Well, this is interesting. What the hell? Why don't we have audio?
Might have to send it to the HDMI output.
I think it's already going on the TV, you just gotta turn the volume up.
TV's down.
TV sucks. Go back to your audio sources.
It was working last last night on my TV.
Let me see.
Go ahead. Feel free.
That was right there. Is that good?
Oh, I'm thrilled.
Put your headband on.
Well, as I was afraid of, either A, they're not transmitting, or B, I don't, anyway. Well, let's go. No, I know which stations. Okay. Yeah, this is New Orleans. Nothing seems to be working right. Okay, this is a waterfall display. But I'm not happy with this at all, to be honest with you. This is the audio spectrum, and it's all noise. If they were transmitting, we'd actually be able to hear them on that frequency, and I don't know. Like I said. Okay, well, I'm not really happy with the way this part of the demo is working out, but let's go to something I can control a little bit better. Okay, well, this is all nice and dandy, but I'm kind of interested in ham radio, so I decided to make a receiver for 2 meters. So, this is my 2 meter receiver. And it's a little bit simpler in some ways, because I take the output right here. Y'all can see the cursor, right, when I do that? Okay. You can see I take the output of the receiver and feed it directly to the FFT sync. Not a problem. And also I split it and I send it to a scope and I send it to a constellation display. Anybody familiar with constellation displays? That's where you can actually display a quadrature signal. And then the waterfall, and those are different modules that, like I said, you literally take them from the box over here on the right hand side, drag it over and connect it up. And then down here at the bottom I added I had to add all of this just so we could listen to it. And that is, this is the receiver up here, and I'm sorry, that's a low pass filter, excuse me. I had to have, to massage the signal enough to hear it, comes out of the SDR, goes into the low pass filter, which is set at a cutoff frequency of 6 kilohertz, which is, as everybody knows, about twice the frequency of the audio, voice audio, the Nyquist frequency. And the next thing we have is a rational resampler, which interpolates 16K, kind of expands it, then it breaks it back down with a decimation of 256K, massaging the data so that it is the right size to fit into the next module, which is the Narrowband Fm receiver module. And then the output of that has to go through a high pass filter with a decimation of 1 and a gain of 1 and a sample rate of 16K and a cutoff frequency of 15 cycles, so you don't get really low. I'm not sure exactly why you need this, but I'm sure you do, because I found it doesn't work right without it. In any event, again, I'm sorry, I'm not the total expert on this, but I think that this is worthy to show you how this works, because this is a lot of fun to play with. And finally, we have the audio sync, which is your speaker. So we're going to run this, and we're going to do a couple of things differently than the last one, because I have some control. Again, it takes a while for Python to come up with stuff. But you got to remember, it's actually, while this is going on, it's writing the program out. You can take that program and run it by itself, by the way. Okay. This is a fast Fft plot, and there doesn't seem to be a lot going on, but let's go to the waterfall. And for this demo, I brought a radio. As you can see, there's not much going on there. This is what a constellation looks like without anything going on. And also we need to do this. And also it has a scope. This is all noise right now. We're going to go down here to the frequency. And I do have a slider somewhere, but for some reason I can never find it when I need it. And what I'm going to do is I'm going to set this up for the Stennis repeater frequency. Because it's on my machine. Okay. All right. Okay, now, as you notice, I changed it down here numerically, and I didn't use a slider. And if you'll notice right here, it centers on 147.2. Okay, let's see how that works. Someone say something? I'm talking to myself when I listen. KG5NXY, radio check. Okay, what you saw was it took and demodulated that signal and showed you the components of my signal. Let's go to the waterfall. Now this is KG5NXY with a radio check. Pretty cool, huh? This is the one I like the best because constellations and quadrature is hard to understand. So I thought, well, this maybe makes it a little easier to understand. As you can see, it actually shows 4 quadrants when it's in its quiescent state. KG5NXY for a radio check. Testing 1, 2, 3. Kind of neat. And then of course we have the scope. With KG5NXY with a radio check. That I'm sure everybody's familiar with. I don't really have too much more to say. I can go on about little details, but I'm going to turn this off.
So why didn't we hear your voice coming out the speaker?
You know, here's the thing about it. I'm not sure. First off is, I'm set at the Stennis frequency. Actually, I did it wrong, to be honest with you. I have it set at Stennis frequency, so my actual transmit frequency was off by 600 kilohertz. In fact, that's what you saw on the far left side. For you to hear my voice, I would have had to made it to Stennis and back. And with my 15-inch Nagoya, which doesn't fit in my backpack, I can use a 5-watt on my front porch to talk to Stennis all day long. But anyway, that's why you didn't hear my voice, because I didn't do the demo right.
So you didn't hit the repeater, is that what you're saying?
That's right.
Okay, all right.
But my main point was to show the demodulation stuff and show how simple that can be. You know, again, I refer back to my original diagram here, my original flowchart, excuse me. I mean, it's literally this simple. If I were to take these 3 components out, the 2 sources, and I don't even need to do that. I'll give you an example. Let's do it this way. Where's the new thing? New. Nothing fits on this screen. Okay. A new WX GUI. This is how you make one. Then you have a... Sorry, guys. There you go. All right. Now, you click on this. Then you can click on your... Then if you want to look up the Sdr source, you'll see that I use a search term, Sdr, brought up a list of sources. In this case, this is the one we're using. So I click that, drag it over, drop it here. All right. Then,
I got a question.
yes.
What is the program that you're using here?
Oh, I keep saying GNU Radio Companion.
That's a software package?
It's part of GNU Radio.
Okay.
GNU Radio is free software created
And
by a...
it implements Python code that you generate.
Right. I don't write anything in this example here.
And these boxes,
Or modules.
okay, and so you just string
Wha-
them together.
That's it.
So how do you know what you're doing?
You have to study.
Like a jigsaw puzzle.
It's not.
I just couldn't
It's
read.
not.
I can't read what's in the boxes, so
That's fair.
totally at a-
I can't read it either. I mean,
I do as well with the screen up.
well, I'm glad we got that, to be honest with you, because there's going to be a really bad demo without it. And I'm not sure it's been a great demo, but in any event, it would have been a lot worse if I didn't have something to show you guys. But anyway, let's get back to building one, okay? Show you how simple it is to build stuff. Okay. Now we've got the full thing again. Let's go look at our GUI components. We have QT and WX. For our use, we're going to use WX. Again, those are two different types, two complete sets of components. They basically have the same things, mostly. WX is being phased out, they say, but it still has some things that that are good for this demo. And so, and I forgot my mouse, so of course that always makes it easier. All right. Okay, so we have, that's not what I wanted. I want sinks. S-I-N-K. Everything's a matter of sources and sinks. All right. Going down the list. Okay. Here we're going to pick the WX GUI FFT sync. And what the heck. Let's just, oops. Got two of them. And we just connect them together. Click on that one. Click on that one. Try again. There you go. And you can move them around, do what you want with them. Okay. And that's really all you need. Oh, let's do one more thing. Let's change this to something that we can all recognize here. That has a nice clean signal, maybe. 99.5 megahertz. Nice, strong FM radio station. Okay. Got to give it a name. Call it Symposium. Simp. And there it is. And yeah, can't really see it that good. If you were looking at if I had a better antenna, perhaps you'd see a better signal. But as you can see, this is the center frequency in the middle, and this particular channel has a couple of additional sub-channels. Yeah, right.
What's the bandwidth we're seeing there, plus or minus?
It's about 20 megahertz here, but in this case, actually it's showing 15 megahertz band. Minus 15, plus 15. That's right at the upper limit for this box here. It's a little bit less than that, really. Anyway, but again, you can see the center is being modulated, and of course, the two subcarriers. But the whole point of that is, look at all it takes to make it. So, and I know that when I got back into ham radio, I was fascinated by waterfalls. And I guess we've all, you know, you pay big bucks for a waterfall display on the radio these days, right? Oops. Yeah, you pay big bucks for it, but oh, something's wrong. What did I do wrong? I may not be able to make this work. It says it can't generate the block. And I do not know what the problem is.
You select QT, you would waterfall.
Thank you. You're right. I'm glad somebody's paying attention, but did a better job than me. Yeah. Stop moving. What happened to my sinks here? Let's try it again. Sinks. No, I don't want an audio sync. By the way, it doesn't do you any good to put an audio sync in without all that other circuitry because you can't. Yeah. Come on, where's the sync at? Ah, there you go. Well, it's supposed to be very simple, slick. Look, guys, all you gotta do is this. Oh, well. Look, guys, all you gotta do is this to get a waterfall. Ta-da! So,
So the two sort of bars on the left of the center, that's the subcarriers?
yep,
Okay, and then the middle is the voice or
that's right.
music or whatever they're playing.
Yep. Okay, guys. So, my whole point here was to show you how easy it was to get into SDR and how cheap and easy. And I hope I at least opened some doors for you guys. And I'm ready for. Thank you.